Okay, now we're going to start working with inclines here. So notice that we're given a frictionless interface. So we still have a lot of simplifying factors here. The interface block, the interface between the surface and block one there is frictionless. The cord is massless. The pulley is massless and frictionless. And we're given the two block masses and we're given an incline angle that I need to write in here. That's theta. There's our pulley. We are asked to determine the acceleration of the blocks and the tension in the cord. So our givens are M1, M2, and theta, and we're asked to find acceleration of the blocks and tension in the cord. This is, I think, a pretty neat problem because you don't know any relationship between those masses. Like I've obviously drawn M1 as like a bigger blob than M2, but um, that doesn't, we can't necessarily take anything from that. We don't necessarily know anything else about that's the situation. So I like this because what I want you to be thinking about here is like, say you were coding this and you wanted to make some kind of model, right? That the user could put in the mass of each block and the user could put in the angle of incline, say, with these other conditions in place. And then what your program would do is it would calculate the acceleration of the blocks and the tension in the cord. So you what we want to make sure is that like what could this work? Would the user be able to break the software, right? Like, can we make this so that we have a robust solution, is what I'm trying to say. A solution that is really general, and a general solution is a powerful solution. So, if I only have a solution that works if M2 is greater than M1, that's okay, but it's not as good as a solution that works regardless of the relationship between M1 and M2. I hope I'm making that clear. So it was on purpose that I left that ambiguity in this problem. I think it's good to consider, and then we'll see where it takes us as well. So because we're on an incline, we need to use a rotated coordinate system for block one. And I'm going to remind us what that looks like. So I'm just going to overlay on top of, this is what I consider to be my physical diagram. I'm going to overlay a coordinate system. I don't usually do this, but that's because we normally are all vertical and horizontal. And now we're embarking on this part of our journey where not everything is going to be always vertical and horizontal, because in the world, not everything is. And this is important to us because the force of gravity is always pointing toward the center of the planet. And we call that basically vertical, right? So it matters when we rotate a coordinate system. So I'll go ahead and rotate in this direction for my block M1. And then for block M2, I'm just going to use vertical and horizontal here. So the question might be, what's my motivation? Why would I rotate? Do I just rotate automatically every time I see an incline? What happens there? And my answer is no, you don't rotate every time you see an incline. The motivation is looking at the direction of acceleration. So M2, block two, is going to be accelerating vertically. And we don't know from the given information if it's up or down, but I do know that what block two does is it basically has vertical motion. And block one is going to be accelerating along the incline. So what I want to do is I want to keep the acceleration in all cases that I can, keep the acceleration on axis. So we want on axis acceleration. In order to do that for block M1, I need to rotate my coordinate system. So I'm going to do that. I need to, in order to fully flesh out my coordinate system here, I need to choose some sign conventions. So here I have to pick. Again, I don't know which mass is bigger. It's not given in this problem, but I still like, if I'm going to make progress on this problem, I need to pick a sign convention and I need to go with it, right? So what I'm going to do for M1 is I'll say my positive y is upward here, and I'm going to say positive x is to the right. I don't really have room to write that in with that string there, so I'm just going to say negative x is to the left here. So you can kind of see those directions. So positive x is to the right. For my mass M2, then I want to be consistent here. So when mass M1, if it accelerates to the right, then mass M2 is going to be accelerating downward. So I'm going to choose here positive y to be downward for M2. Okay. So that's a choice. If it helps you, I can put the positive x this way here. So you can see that's to the right for block one, and then the positive y is downward for block two. You can, if it really bugs you, you can call that positive x downward for block two, but I like to really reserve y for vertical and x for horizontal. Okay, so we've got that down. Now let's go ahead and draw our free body diagrams. We know that that's the next thing we need to do. So free body diagram for block M1, that's the block that's sitting on the incline. And then I'll draw the free body diagram for block M2. That's the block that's hanging. That one will certainly be a lot simpler. Okay, so block M1, we know we've decided that upward and rightward are positive there. And for block M2, downward, that's only a one-dimensional motion, so I don't need to label. I'm not going to have any horizontal forces on block M2. It's just hanging there, right? So I don't need to label a sign horizontally. So let's fill in our forces here. Look at the block that is sitting on the incline. Let's start that one, even though it's more complex. What is it in contact with? Well, it's in contact with the chord. That's going to be a rightward force there on it. I can call that T for tension. It's in contact with the surface beneath it, and that surface beneath it is exerting a normal force, and the direction of that normal force is normal or perpendicular to the surface. So for my rotated coordinate system, that's going to be straight up. So that'll be the normal force. That's the only normal force in the problem, so I don't need to subscript it. And so that's all. Those are the only places that block one is in contact with anything. It has the surface beneath it that's touching it. There's no friction there. So the only other type of force that can be exerted by a surface is normal force. I've got that taken care of. And the string is touching it. That's the tension. I have that recorded. So those are our two contact forces. Then we have our one invisible force, which is weight. Now, weight, regardless of what we do with our coordinate system, weight is always directed toward the center of the planet, which we call downward when we're near the Earth's surface, as we are here. So I need to put that accurately on my free body diagram. So where that's going to sit is like right here. And here is the angle theta. M1G is the magnitude of that weight, right? The mass of that block, M1, multiplied by gravitational acceleration. All right, so those are the only three forces. If that totally threw you for a loop, those directions, go back over to the rotated coordinate system on the physical diagram and look at them there. I'll draw them in there. So here, if it helps you, tension is directed to the right from the block, right? The string is pulling the block to the right. The normal force, the force of the surface underneath the block, is exerting a normal force. Normal forces are always perpendicular to the surface. So that one is being exerted perpendicular to the surface. We'll call that N. And then, of course, you have the weight of the block that, regardless of everything else that's going on, is always directed straight down. And that is going to be M1G. That's the weight of that block. This little angle inside here, that angle is the angle theta. So if you have trouble with those angles, you can spend some time just on that. I would like go spend time just on that and make sure that you can see. You can, there are various ways of drawing that out. All of us, our brains work a little bit differently. So for some of you, looking at similar triangles is going to help. For me, my brain works best when I have something physical right in front of me or when I can picture something that's actually physically happening. That's much better for me than just like some kind of concept. So, what I imagine, and this might help some of you that are a little bit more inclined physically, is that you can consider that vector that's always going to point in the direction of weight. Think about it like a string with like a weight at the end of it, right? A string with a little plumb bob or something at the end of it. And that string, no matter where you put it, no matter what happens with your coordinate system, it's always going to point to the center of the earth. And that needs to be the case always with your weight vector. So if I can consider my incline as like a book or something that I can open and close, think about what happens as you adjust the angle of the incline theta. what happens to the theta in between the weight vector and the y-axis? Kind of play with that in your mind. If that's still tough, build it. Take a book. I mean, this isn't that tough to do that. You can just take a hardback book, right? And attach a string with a little pen or something attached to the end of the string and attach that to the front cover of the book and then open and close the front cover of the book and keep an eye on what that string does versus the angle of the book. Okay, different ways to get that. I know sometimes students get a little bit hung up on that angle theta. Moving on, those are all the forces then on block M1, block M2. What do we have? Well, we have the only thing touching it is the string. So that's providing an upward force T. And then we have, of course, the weight of block 2, M2G. Fairly simple for that body. And then we can go ahead and use Newton's second law here. And I'll do that for M1. And now here, notice that I'm going to look at both the X and Y. I'm just going to do that because we have some off-axis forces here. So if I'm going to sum my forces in the X here for M1, what does that give me? T. Now minus a component of the weight. So notice the weight that it has both an X and Y component. I'm going to just switch colors. I won't do a whole lot of this because it's assumed that we kind of have our vectors down, you guys, but I'll do this just for this one time. Here is the X component of the weight, right? And here is the Y component of my weight. Yeah? Cool. So when I'm summing up my X forces, T minus, now I need here just the X component of the weight, which is going to be M1G sine theta. I'm looking for the opposite side of the triangle, so that corresponds to the sine. That's it for X. That'll be equal to M1 times what I'll call A sub X, which is the acceleration in the X direction. And now I'm going to sum my Y forces for this one. I have upwards positive here, so N minus now the Y component of the weight, which is M1G cosine theta, and that's equal to M1 times AY. Now, what I want you to notice here is that this block M1, is any acceleration that happens is happening parallel to the incline. There is no acceleration that is happening perpendicular to the incline. So there is no y acceleration, or the y acceleration is actually equal to 0 here. So what that tells me is this equation down here just renders me this n minus m1g cosine theta is equal to 0. That's what I get there. Okay, so whether that's useful or not, I don't know, but I'm just going to kind of leave that there. Since my y acceleration is equal to 0, what I'm going to do is I'm going to go back and I'm going to change this acceleration, take off the x subscript. I really just have one acceleration to worry about. And because these two blocks are connected by an inelastic cord, they're going to move together. So that means that their acceleration magnitudes will be the same. So now let's look at the hanging block. I have then M2G minus tension. Again, we have downward positive here, right? Our acceleration is downward for that block for the direction that we picked is equal to M2A. All right, so I have my two equations there, and I should be able to move forward from there. Let's pause, and at this point, I always like us to consider what our unknowns are. So what don't we know? What's not given in this problem? The tension is not given in this problem, and the acceleration is not given in this problem. So I have two unknowns and I have two equations. So I'm pretty happy there. That works. Um, we do have, technically, you might be saying, hey, Stephanie, we have a third equation because we have this equation here from our FY. But as it turns out, in this problem, we can render this equation. This equation isn't useful to us in this particular problem. As soon as we start dealing with friction, then it will be useful because it turns out that the frictional force, the magnitude of the frictional force is dependent on normal force. But for right now, we're not going to use this. So actually what I'm going to do is I'm going to go ahead and get rid of these here. It's kind of good practice to do it, but it's not something that we're going to use for our analysis for this problem. So we have two equations and two unknowns. I know now that I can find the acceleration. And when I do that, what I'm going to get, so again, I'm going to leave the algebra to you, figuring that out. And notice this problem is, oh no, it is also asking for the tension. We can solve for both of those. But for right now, I want to discuss for just a moment what you get when you calculate acceleration. And you'll get an expression that looks like this. You take a moment and write it out. That's all over m1 plus m2. So again, going back to the fact that like think about we would want to model this in a way that a user could we could like code it, say, and then a user would be able to put in masses and then they'd be able to get some useful output out of this. So look at this expression now and ask yourself like does this make sense? Would this be useful? So the way that the sign convention that we used would say that like our acceleration here would be positive as long as now look at the I guess that term up here in the top. This is the term here that can change the sign of the entire expression, right? That's in parens there. So that can change the sign of the entire expression. Nothing else can. If you look at the denominator, those are both positive. Nothing's going to change the sign there. But basically, what this is saying is that as long as m2 is greater than m1 sine theta, then block the acceleration is going to be block m1 will accelerate to the right or up the incline, and block 2 will accelerate downward. If we have the case that m1 sine theta is greater than m2, that renders this entire acceleration negative, right? And it doesn't mean it's broken. All that means is that the outcome is that the mass m1 is going to accelerate down the incline, and the mass m2 is going to accelerate upward toward the pulley. So that's a possible outcome. Sure, it depends on the proportions of the masses. And you see, it's not as simple as is mass 2 greater or mass 1 greater, because that incline throws a little bit more complexity into that. You can see that there's a third case here. There is an acceleration equals 0 case. What if we had m2 equal to m1 sine theta? That one case, right? If you have that one special case, if the user were to put that in, then what it would let them know is that the system would not accelerate. It's not that it wouldn't move, say the system was initially in motion, it's just that the velocities would remain constant. So kind of picture that in your mind. So I like this problem because it allows for all those cases. It's not quite so confined. So that is our expression for acceleration. This problem is also asking you to express tension, and what you should get for tension, again, this is algebra party, is simply m2g multiplied by, pretty big expression here, 1 minus m2 minus m1 sine theta. So you'll recognize this from your acceleration over m1 plus m2. So there we found both our acceleration and tension as requested in the problem.